Welcome to For Science Salah Lotfy channel. What if I told you that a simple piece of glass can remember radiation, not record it electronically, not calculate it digitally, but physically change its color and structure to reveal exactly how much radiation it has absorbed? Today's episode takes you inside the world of electron beam irradiation and advanced radiation-sensitive glasses. We are exploring a new generation of vanadium-doped Borate glasses, materials that respond to radiation in a clear, measurable, and reliable way. As electron beams pass through these glasses, atoms shift, electrons rearrange, and invisible radiation becomes visible data. Color appears, optical properties change, defect centers are created, each one carrying information about absorbed dose. In this episode, you will discover how radiation reshapes glass at the atomic level, why vanadium is the key to radiation sensitivity, how scientists use light, spectra, and electron spin to measure radiation, and why this research matters for medical sterilization, food safety, and industrial radiation technology. This is not theoretical science. This is applied radiation chemistry with real industrial impact. Let's begin.
Welcome to For Science Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة، مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy channel، العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Welcome to For Science Salah Lotfy channel. Today, I'm diving into a fascinating study that sits right at the crossroads of radiation chemistry, materials science, and real-world industry. The spotlight is on Borate glasses, specifically, what happens when you zap them with electron beams. The research I'm talking about is called The Impact of Electron Beam Irradiation on Some Novel Borate Glasses Doped with Vanadium Oxide, Optical, Physical, and Spectral Investigation. It's a mouthful, but trust me, the science is worth it. This work comes from Professor Dr. Ayman Ebu-Hassin at the National Center for Radiation Research and Technology in Cairo, and it's published in Inorganic Chemistry Communications. Now, let's get to the heart of why this research matters. Borate glasses doped with vanadium oxide aren't just some chemistry lab curiosity, they are strong candidates for something called radiation dosimetry. Basically, they're like high-tech sensors that can measure how much radiation something has absorbed. That's super important for things like medical sterilization, food irradiation, and all sorts of industrial processing. So, what did this study do? Researchers took these new Borate glasses, exposed them to electron beam irradiation, a form of high-energy radiation used everywhere from hospitals to factories, and then checked what changed. They looked at how the glass structure shifted, how the color and optical properties morphed, and how new defect centers popped up inside the material. These changes are not just interesting on a molecular level, they're measurable using advanced spectroscopic techniques, which means these glasses could be used as reliable, precise radiation detectors. Let's talk timeline for a second. The team started this journey in August 2022, revised in November, and had the research accepted and published, all in the same month. That's fast-track science, reflecting just how relevant and urgent these findings are. Here's why this matters to you. Whether you're a science student or an industry professional, understanding how radiation transforms materials isn't just academic, it's the foundation for building safer hospitals, improving food safety, and optimizing industrial processes all over the world. These glasses could turn invisible, dangerous radiation into clear, measurable signals, making the invisible visible. In the next parts of this episode, I'll break down the science step by step, unpack the experimental techniques, and show you how these results could change both science and industry. So, stick around and stay curious, because at For Science Salah Lotfy channel, we're all about turning cutting-edge research into real-world impact. Hey there, science fans! Whether you're a curious student, a tech enthusiast, or just someone who loves learning about the hidden forces shaping our world, you're in the right place. Welcome back to the channel. Today, I'm tackling a question that's way more important than most people realize. It's a topic that quietly impacts our daily lives, our health, and even the safety of the technology we depend on. Radiation. It's everywhere in modern technology, whether you're thinking about sterilizing medical tools, preserving food, or even tweaking the properties of high-tech materials. From hospitals to research labs, and even in the food industry, radiation is a powerful tool that helps us achieve things that would otherwise be impossible. But here's the thing. Controlling how much radiation is used. That's not just a detail, it's absolutely essential. Too little, and you might not get the results you need. Too much, and you could damage equipment, materials, or even put people at risk. So how do we actually measure the dose of radiation something absorbs, especially in real-life, messy working conditions? It's not as simple as just pointing a Geiger counter and calling it a day. We need tools that are precise, reliable, and can handle the complexity of real environments. That's where glass dosimeters come into play. These clever devices are made from special types of glass that react to radiation in measurable ways, making them perfect for tracking exposure over time. Imagine a tiny piece of glass that can tell you exactly how much radiation it's been hit with. Sounds futuristic, right? But it's very real, and it's what keeps so many industries safe and precise. These dosimeters are like silent guardians, quietly recording the invisible story of radiation exposure. Today, I want to dive into a fascinating study that's pushing this field even further. Scientists have been experimenting with new types of Borate glass, and here's the twist. They're doping the glass with vanadium oxide. This isn't just a random choice. Vanadium oxide can dramatically change how the glass responds to radiation, opening up new possibilities for detection. Why does this matter? Well, when you shoot this glass with an electron beam, crazy things start happening at the atomic level. The energy from the beam interacts with the atoms in the glass, causing shifts and rearrangements that are both fascinating and useful. The structure of the glass itself morphs and changes, and these changes can actually be measured. Scientists use advanced imaging and computer simulations to track exactly what's happening, right down to the tiniest details. This isn't just about watching radiation do its thing, it's about designing a material that can accurately measure radiation, even in the middle of a busy hospital, a food processing plant, or a materials lab. The ability to monitor radiation in real time, in all sorts of environments, is a game changer for safety and quality control. We're talking about science that literally safeguards lives and innovations. Every breakthrough in this field means better protection for workers, patients, and the public, and more reliable results for researchers and industry. By the end of this episode, you'll get the inside scoop on why Borate glasses are the superheroes of radiation dosimetry. They're not just passive materials, they're active participants in the quest for safer, smarter technology. You'll see how electron beams mess with glass structure in ways you can't see but scientists can track, right down to the atomic level. It's like having X-ray vision into the world of atoms and molecules. And you'll find out how these invisible changes, optical and spectroscopic, transform an ordinary-looking piece of glass into a sensitive, reliable radiation sensor. These sensors are the unsung heroes behind the scenes, making sure everything runs smoothly and safely. So buckle up, because we're about to crack open the atomic secrets of Borate glasses and see how a little chemistry can revolutionize the way we measure radiation. Get ready for a journey into the invisible world that keeps us all protected. Let's get into it.
Let's kick things off with a question I always ask myself. Why glass? And more importantly, why borate glass? It's a material that might seem ordinary at first glance, but when you dig a little deeper, you'll find it's packed with some truly remarkable properties that make it a favorite among scientists and engineers alike. When it comes to radiation chemistry, borate glass isn't just another material on the shelf. It's actually a superstar. And here's why. Its unique combination of physical and chemical traits sets it apart from other types of glass, making it a go-to choice for a wide range of scientific applications. First up, the effective atomic number of borate glass is super close to that of human tissue. This means that, when exposed to radiation, borate glass responds in a way that's strikingly similar to how our own bodies would react. Why does that matter? Well, in medical dosimetry, where you need materials that act like human tissue under radiation, borate glass is pretty much the perfect stand-in. It allows researchers and medical professionals to simulate and measure radiation doses with impressive accuracy, which is crucial for both patient safety and effective treatment planning. But there's more. Borate glasses are easy to prepare, low in cost, and, get this, they're chemically flexible. You can tweak their composition to suit different needs, which is a huge advantage in research and industry. Plus, their production doesn't require exotic or expensive raw materials, making them accessible for labs around the world. Their secret weapon is their structure. They can switch between threefold and fourfold coordination. Think V₂O₅ and V₂O₅, so the glass network can actually adapt when you hit it with stuff like radiation. This adaptability means borate glass can absorb and respond to energy in ways that other glasses simply can't, making it incredibly versatile for scientific experiments. Now, here's the catch. Pure borate glass isn't perfect. It's got a bit of a weakness. Its chemical durability is on the low side. That means it can break down or dissolve more easily when exposed to certain environments, which could limit its usefulness in some applications. But that's where science comes in. By adding just the right metal oxides, we can boost the stability without sacrificing the glass's sensitivity. These additives strengthen the glass network, making it more resistant to chemical attack while still preserving its unique radiation response. So, when you put all that together, tissue equivalence, easy prep, adaptability, and improved stability, borate glass stands out as a top contender in radiation chemistry. It's a material that continues to inspire new research and innovation, opening doors to safer medical treatments and more precise scientific measurements. That's why borate glass matters. It's not just a tool, it's a bridge between science and real-world impact, helping us push the boundaries of what's possible in medicine, research, and technology. Hello, science fans! Today we're exploring a remarkable kind of glass, engineered for a special purpose. This isn't your average window glass. It's built from a precise recipe, where every ingredient matters. The goal? A glass that's strong, stable, and sensitive to invisible radiation. Scientists carefully select each chemical, like building with Lego bricks. Each piece adds strength, stability, or a unique property. The foundation is boron oxide, supported by oxides of lithium, sodium, calcium, strontium, and aluminum. Each oxide brings something special: durability, stability, or a lower melting point. But the real secret is a tiny amount of vanadium oxide, just 0.2% or 0.3%. That's like a sprinkle in a giant cake, but it transforms the glass into a sensitive detector. This process, called doping, fine-tunes the glass's properties. With this careful mix, ordinary materials become extraordinary. The result? A glass that's not just tough, but can sense radiation, thanks to that tiny pinch of vanadium. It's a scientific recipe with a powerful twist. Let's see how each ingredient plays its part. Meet our chemical cast. Boron oxide forms the backbone, a strong, stable network. Lithium and sodium oxides act as modifiers, loosening the structure so the glass melts at lower temperatures. Calcium and strontium oxides step in as stabilizers, toughening the glass and protecting it from damage. Aluminum oxide boosts hardness and chemical resistance. Tellurium oxide is the wild card, lowering melting temperature and increasing density. Each ingredient is measured precisely, creating a balanced, high-performance material. This collaboration makes the glass durable, efficient to produce, and ready for its special mission. All these elements set the stage for vanadium, the secret agent that gives the glass its superpower. Its chemistry working in perfect harmony. Now, let's see what that pinch of vanadium can do. Here's where the magic happens. Vanadium oxide. Vanadium is a transition metal, able to switch between different states, like a superhero with multiple powers. In the glass, it usually sits quietly as V₂+, but when radiation hits, it transforms to V₄+. This change alters how the glass absorbs light, so scientists can measure radiation exposure by tracking this shift. The more radiation, the more vanadium changes state, and the bigger the effect. By adjusting vanadium's concentration, scientists fine-tune the glass's sensitivity. It's a tiny tweak with a huge impact, turning glass into a radiation memory device. That's the power of a pinch of vanadium. Let's see how this superglass is made. Making this glass uses an age-old method, melt quenching. Scientists mix the powders, heat them in a crucible, and melt them at much lower temperatures than regular glass, thanks to the SMART recipe. Lower melting means less energy, lower costs, and a smaller carbon footprint. The molten mix is rapidly cooled, locking atoms in a glassy state. Then, it's gently reheated and cooled again to relieve stress, making the glass strong and stable. This efficient process makes radiation-sensing glass affordable and sustainable. It's a win for science, industry, and the planet. Keep exploring, there's always more to discover. Alright, before diving into how radiation messes with materials, let's get one thing straight. Are we actually looking at glass? Or is there a bit of sneaky crystal hiding in there? It might sound basic, but trust me, this question can make or break all the science that comes next. So, how do I figure out if these samples are truly glassy, not partly crystal? X-ray diffraction. It's like giving your material a full-body scan, but instead of bones and organs, I'm searching for order. Crystal order, that is. Here's how it works. I shoot X-rays at the sample, and I look at the pattern that bounces back. If there's a regular, repeating atomic structure, like in a crystal, you get sharp, spiky peaks in your pattern. But if the atoms are arranged totally randomly, like in glass, those sharp peaks disappear. All you see is a broad, gentle hump. That's the X-ray fingerprint of an amorphous material. So, what did I see in my samples? No sharp peaks. Just big, broad, fuzzy humps. That's the signature of fully glassy material. No crystals lurking anywhere. It's like the difference between a choir all singing the same note, that's a crystal, and a crowd just mumbling and chatting, that's glass. The mumbling pattern is what I want. But why does this even matter? Well, when I blast these samples with radiation, how they react totally depends on their atomic structure. In crystals, atoms are locked in a rigid grid, so defects and disruptions are rare and kind of snap back into place. But in glass, where everything's looser and more disordered, radiation can cause all sorts of havoc. Bonds break, defects form, atoms rearrange. It's a bit of a chaos party in there. So if I didn't confirm my samples were glass, my whole experiment could be off. I need to know exactly what I'm working with, because the way radiation interacts with glass is way more dramatic than with crystals. That's why X-ray diffraction is my first stop. It tells me, without a doubt, that I'm dealing with the real, fully glassy deal. And hey, if you found this peek behind the science curtain helpful, don't forget the flowers, hit subscribe to For Science Salah Lotfy channel, and keep riding along for the next chapter in this story. What happens when you zap glass with a superpowered beam of electrons? Welcome to the world of electron beam irradiation. Imagine a stream of electrons, accelerated to nearly the speed of light, slamming into materials and causing dramatic changes. We measure the energy delivered in kilogray, or kGy. Today, we'll see what happens at 3, 5, and 8 kGy. Electron beams are used everywhere, from sterilizing medical equipment to preserving food, all without chemicals. In materials science, electron beams can make plastics tougher and more heat-resistant by cross-linking their molecular chains. But what about glass? Its atoms are arranged in a jumbled, frozen liquid structure, making it uniquely reactive to electron beams. When hit by these high-energy electrons, glass can fundamentally change its properties. We're about to dive into the atomic world of glass and see how a simple zap can make it colorful. Get ready. Things are about to get electrifying. Let's zoom in on glass at the atomic level. It's mostly silicon and oxygen, linked in a network. When an electron beam hits, it knocks electrons out of their atomic homes. This is ionization. The freed electrons and the holes they leave behind zip around, looking for places to settle. Glass isn't perfect. It has defects like non-bridging oxygen atoms, prime spots for trapping these charges. Sometimes, the beam even knocks entire atoms out of place, creating vacancies and more defects. These defects act as traps, capturing electrons and holes to form color centers. Color centers absorb certain wavelengths of light, so the glass starts to interact with light in new ways. The result? The glass is no longer perfectly clear. It's gaining color, all thanks to atomic-level chaos. This is the secret behind the magic. A zap of electrons, and suddenly, glass can change how it looks. Let's see what happens as we increase the dose. At 3 kGy, the electron beam gives glass a gentle but noticeable push. Enough energy is delivered to create lots of electron hole pairs, which start filling up defect traps. If the glass contains vanadium ions, they're great at trapping charges and changing their state. Non-bridging oxygen hole centers, NBOHCs, also form, absorbing green and blue light. The visible result? The glass takes on a yellowish or light brown tint. This subtle color change is the first sign of atomic events made visible. Millions of tiny changes add up to a transformation you can see. At 3 kGy, the effect is clear but not overwhelming. A perfect introduction to the phenomenon. The glass's colorful story has just begun. all thanks to a beam of electrons. Science in action. Now, let's crank up the dose to 5 kGy. More electrons, more ionization, more defects. The glass gets crowded with color centers, deepening the brown tint. At 5 kGy, the color is much richer and darker. More energy means more light absorbed. Higher doses can even create new, complex defect centers, absorbing different wavelengths and darkening the glass further. Push it to 8 kGy, and the glass faces an intense storm of energy. Nearly all available traps are filled, and the glass absorbs a broad range of visible light. The result: a deep, dark brown, almost black, with dramatically reduced transparency. The journey from 3 to 8 kGy shows a clear, dose-dependent transformation. By controlling the electron beam, we can precisely tune the color and optical properties of glass. It's a powerful demonstration of atomic scale cause and effect. We're literally painting with electrons. So, why zap glass with electrons? It's not just for show. The predictable color change makes glass a perfect radiation dosimeter, measuring exposure in hospitals, labs, and power plants. By reading the darkness, scientists know exactly how much radiation the glass received. This research also helps us design better, radiation-resistant materials for space technology, ensuring satellites and spacecraft survive harsh environments. Artists and designers can use irradiation to create unique glass colors and patterns, fusing art with quantum physics. Electron beam irradiation unlocks new properties in everyday materials, from safety to creativity. It's a reminder that even simple glass hides a complex dynamic world. By understanding and controlling these atomic processes, we open up new possibilities for technology and art. Next time you look through glass, remember the invisible atomic dance inside. Science makes the ordinary extraordinary.
Imagine if I told you that ordinary glass, the kind you see in windows or lab equipment, could actually change its color when exposed to radiation, almost like a chameleon blending into its surroundings. It sounds like science fiction, but it's a real phenomenon that scientists use to their advantage in the lab. This isn't just a party trick, it's a powerful tool for measuring radiation, and it all starts with a simple, clear piece of glass. Take a look at these glass samples. Before they're exposed to any radiation, they're almost completely invisible, so clear and pristine that you might not even notice them sitting on the lab bench. They look just like any other piece of glass you've ever seen, with no hint of what's about to happen. But once these glasses are hit with a powerful electron beam, something remarkable happens. Over time, they begin to darken, shifting from transparent to a deep, rich brown. The more radiation they absorb, the darker they become. It's almost like watching a photograph develop in a darkroom, except here, the developer is pure energy from radiation. This dramatic color change isn't just for show, it's actually a visible sign that radiation is interacting with the glass at a microscopic level. The glass is acting as a silent witness, recording the invisible energy it's been exposed to by changing its appearance in a way we can see and measure. To understand exactly what's happening, scientists use a tool called UV visible spectroscopy. This technique lets them see how the glass absorbs different wavelengths of light. After irradiation, the glass shows a sharp absorption peak at 290 Dau with 300 nanometers and a broad absorption band near 580 nanometers. These changes in the absorption spectrum are like fingerprints, revealing the presence of new color centers inside the glass. But what's causing these new color centers to form? The answer lies in the chemistry of the glass itself. Many of these glasses contain vanadium ions, which are sensitive to radiation. When the glass is bombarded with high-energy particles, the radiation actually changes the oxidation state of vanadium ions, transforming V5+ ions into V4+ and even V3+. This shift in electron configuration creates new sites in the glass that absorb light differently, leading to the dramatic color change we see. This unique property makes these glasses incredibly useful as dosimeters, devices that measure the amount of radiation exposure. By simply observing the color change, or by measuring the absorption spectrum, scientists can determine exactly how much radiation the glass has absorbed. This is crucial in environments like nuclear power plants, medical facilities, and research labs, where monitoring radiation levels is essential for safety. So next time you see a piece of glass, remember it might be more than just a window or a beaker. It could be a high-tech tool for keeping people safe from invisible dangers. And hey, flowers, don't forget to subscribe to the For Science Salah Lotfy channel for more amazing experiments and discoveries from the world of science.
Hey, science fans! Ever wonder what makes glass so unique? It's everywhere. Windows, phones, labs. But it has hidden secrets. Glass talks to light and energy through 3 key properties. First, the optical band gap. An energy barrier electrons must cross. A bigger gap means it's harder for electrons to get excited. Next, Urbach energy, a measure of how messy or disordered the glass is at the atomic level. More Urbach energy means more chaos inside. Finally, the refractive index. How much glass bends light? A higher index means light slows down and bends more. These 3 properties, band gap, Urbach energy, and refractive index, are like glass's vital signs. By measuring them, scientists peek into glass's invisible world. They reveal how glass will react to light and energy. Understanding these basics unlocks amazing science. Let's dive deeper. Now, what happens when glass meets radiation, like gamma rays? Radiation shakes up the atomic structure, causing big changes. The optical band gap shrinks. Electrons need less energy to get excited. Urbach energy rises, signaling more internal disorder. Radiation acts like a wrecking ball, breaking atomic bonds and making the glass even messier. The refractive index increases too, as the glass becomes denser and bends light more. So, radiation makes glass more chaotic, more light-bending, and more sensitive to energy. These changes aren't just numbers. They're clues to what's happening inside. The glass transforms, gaining new properties. Scientists use these shifts to understand and control glass in extreme environments. It's a fundamental transformation at the atomic level. Science in action. Let's zoom in. What's really happening inside the glass? Glass is a network of atoms, often built from triangular V₂O₅ units connected by oxygen bridges. Radiation breaks these bridges, creating non-bridging oxygens, dangling atoms that disrupt the network. More non-bridging oxygens mean more disorder and higher Urbach energy. Radiation can also turn flat V₂O₅ units into 3D V₂O₅ pyramids, adding strain and complexity. This mix of V₂O₅ and V₂O₅ units makes the structure less uniform. These atomic changes explain the shrinking band gap and rising refractive index. Radiation permanently reconfigures the glass, leaving behind measurable evidence. The glass is no longer the same. It's a new material. That's the atomic story behind the transformation. All these changes make glass more sensitive to energy. New defects and mixed V₂O₅ V₂O₅ units create extra energy levels inside the band gap. Electrons can now hop across the gap more easily, making the glass more optically active. This is why the band gap shrinks and the glass responds to lower energy light. As radiation increases, the glass network becomes more chaotic and fragile. Each new defect makes it easier for the next change to happen, a feedback loop. The rising Urbach energy is a clear sign of growing disorder. By tracking these properties, scientists can predict how glass will behave in harsh environments. It's a powerful example of how tiny atomic changes shape the world we see. The invisible world inside glass is full of surprises. Everything around us is made of atoms, and inside those atoms are electrons with a property called spin. Imagine them as tiny spinning tops. In most materials, electrons pair up with opposite spins, canceling out their magnetic effects and making them undetectable by certain methods. But when this pairing is disrupted, say by radiation, an unpaired electron is left behind, creating a defect in the material. Detecting these defects is crucial for understanding how materials respond to stress, degrade, or can be used in technology and medicine. To find these invisible defects, scientists use electron spin resonance, or ESR spectroscopy. ESR acts like a specialized radio, tuning into the unique frequency of unpaired electrons. It's a non-destructive way to count these defects and measure the extent of atomic-level damage. In a perfect material, all spins are paired and silent. In a damaged one, unpaired electrons create a detectable magnetic hum. ESR detects this hum, letting us quantify the number of defects. This turns invisible atomic damage into measurable data. By measuring the ESR signal, we can directly assess how much a material has been affected by external forces like radiation. This insight is essential for developing better materials and ensuring their reliability. ESR opens a window into the hidden world of atomic imperfections. So, how does ESR work? When a sample with unpaired electrons is placed in a strong magnetic field, those electrons align with or against the field, creating two energy levels. The spectrometer then bombards the sample with microwaves, searching for the exact frequency that flips the electron's spin. When the energy matches, the electron absorbs it. This is the resonance signal ESR detects. Only unpaired electrons respond, making the ESR signal a direct signature of defects. The signal strength is proportional to the number of unpaired electrons. Scientists irradiate glass to create defects, then use ESR to measure the resulting signal. The process is like a roll call for defects. The more unpaired electrons, the stronger the signal. This transforms invisible atomic changes into clear, quantifiable data. ESR makes the unseen world of defects visible and measurable. In a typical experiment, scientists prepare identical glass samples, one as a control, others exposed to increasing doses of radiation. Each sample is scanned with ESR after irradiation. The control sample shows a flat line, no defects. Irradiated samples show peaks in the ESR graph, each peak representing unpaired electrons created by radiation. The more radiation, the stronger the ESR signal. This direct correlation between radiation dose and ESR signal intensity is key. Scientists plot these results, revealing a precise, measurable relationship. The experiment confirms that radiation creates predictable, quantifiable defects. This clarity is essential for using glass as a radiation dosimeter. ESR provides a powerful tool for understanding and measuring atomic-level damage. ESR spectra reveal not just the number, but the type of defects. The position of the resonance peak, or G value, acts as a fingerprint for each defect. Different defects in the glass show up as distinct G values. By analyzing these, scientists identify defects like oxygen hole centers and vanadium-related centers. This detail helps improve material design. Most importantly, plotting ESR intensity against radiation dose gives a straight line, proving the glass's reliability as a dosimeter. ESR turns invisible atomic changes into actionable data. It's a simple, elegant way to ensure safety in radiation environments.
Ever wondered what makes some glass super strong? The answer lies in its molecular structure. Scientists use a tool called FTIR, Fourier Transform Infrared Spectroscopy, to peek inside glass without breaking it. FTIR shines infrared light through the glass, revealing a unique pattern, like a molecular fingerprint. In Borate glasses, we focus on two key structures, V₂O₅, flat triangles, and V₂O₅, strong, 3D pyramids. The ratio of these shapes determines the glass's strength and durability. FTIR shows us how many of each unit are present by displaying distinct bands on a graph. V₂O₅ units appear as a broad band, V₂O₅ units as a sharper one. By measuring these, scientists can predict how tough the glass will be. This is the first step in understanding and engineering super strong glass. What if we blast this glass with a powerful electron beam? This simulates extreme environments like nuclear reactors or space. After irradiation, FTIR reveals a dramatic shift. The V₂O₅ band shrinks, while the V₂O₅ band grows. This means the glass's internal structure is reorganizing. Flat V₂O₅ units are transforming into robust V₂O₅ pyramids. Imagine tiles turning into interlocking bricks. The glass network becomes more connected and stronger. Instead of breaking down, the glass reinforces itself under stress. The increase in V₂O₅ units is direct proof of this transformation. FTIR lets us witness this molecular upgrade in real time. That's how the glass adapts and becomes even tougher. But how do we know if the glass is truly durable? Scientists test it by soaking samples in hot water and measuring weight loss. A tough glass barely loses any weight, proving its resistance. The secret recipe includes boron, oxygen, and key additives: aluminum oxide, calcium, strontium, and tellurium oxides. Aluminum forms strong structures, while calcium and strontium fill gaps, making the network tighter. Tellurium oxide helps create a more cross-linked, resilient structure. Combined, these ingredients build a glass that resists chemical attack, even after irradiation. Hot water tests show minimal weight loss, confirming the glass's enhanced durability. The structural changes seen in FTIR, more V₂O₅ units, translate directly to real-world toughness. Radiation doesn't weaken this glass, it makes it stronger. That's why it's perfect for demanding environments. Why does this matter? This glass is ideal for dosimeters, devices that measure radiation exposure in nuclear plants, hospitals, and space. Dosimeters must withstand radiation and stay stable to give accurate readings, thanks to its robust structure and low weight loss. This glass delivers reliable results, even after heavy irradiation. FTIR analysis explained why. More V₂O₅ units mean greater durability. This isn't luck, it's smart material design, connecting microscopic changes to real-world performance. By engineering the right molecular recipe, we create glass that keeps people safe in the toughest jobs. This Borate glass is a triumph of science and innovation. It's not just a cool experiment, it's a material built for the future.
Hello, science fans. Today we're diving into the world of vanadium-doped Borate glasses, a special kind of glass with superpowers. Imagine a transparent superhero that can measure high doses of radiation precisely. By adding vanadium to Borate glass, scientists have created a tool that's easy to make, stable, and reliable. This glass changes predictably when exposed to radiation, making it a trustworthy tool. It combines chemistry, materials science, and physics to solve real-world problems. The potential is huge, from sterilizing medical equipment to ensuring food safety. This technology is a testament to human curiosity and innovation. By exploring materials, we unlock technologies that improve our lives. So, let's explore this scientific marvel. Get ready for an exciting journey into the world of vanadium-doped Borate glass. How do you make this super glass? Surprisingly, it's straightforward using the melt-quenching technique. Scientists mix boric acid, sodium carbonate, and a precise amount of vanadium oxide. This mixture is heated until it melts into a molten liquid, then rapidly cooled to form glass. The process is simple and repeatable, ensuring consistent properties every time. This glass is incredibly stable, maintaining its structure and properties over time. It doesn't degrade or react with the environment, making it perfect for real-world applications. Borate glasses are strong and durable, and vanadium enhances these qualities. The vanadium atoms integrate into the glass, creating a robust material. This glass is ready to withstand industrial and medical environments. Simple ingredients, a straightforward process, and a rock-solid result. It's a smart and tough material for demanding jobs. This glass is a testament to the power of simplicity in science. A high-tech material from simple powders. How does this glass measure radiation? It's all about the vanadium atoms. When radiation hits the glass, it energizes the vanadium atoms, changing their oxidation state. This change affects how the glass absorbs light, which we measure with a spectrophotometer. Before and after radiation exposure, we test light absorption. The change in absorption is proportional to the radiation dose. This glass works beautifully for doses between 3 and 8 kilograms. It's perfect for industrial and medical applications. The glass records radiation doses, acting as a dosimeter. Its strong, easy-to-read response makes it widely usable. This technology is practical and accessible for quantifying invisible energy, ensuring radiation is used safely and effectively. Where do we use this amazing glass? The applications are vast and crucial for health and safety. In medical equipment sterilization, it ensures the right radiation dose for safety. In food safety, it verifies correct irradiation for extended shelf life. These glass dosimeters provide reliable records for food safety. In manufacturing, they ensure precise radiation doses for material properties. They're used in research, nuclear plants, and more for safety and control. This research showcases the synergy of chemistry, physics, and material science. From understanding atoms to practical tools, it enhances safety and efficiency. Thank you for joining this scientific adventure. For more amazing science, subscribe to the For Science Salah Lotfy channel. Keep exploring and remember, science is all around us. Before we conclude, I would like to express my sincere appreciation and respect to Professor Dr. Iman Ebu Hussein from the Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. On my own behalf, Professor Dr. Salah Lotfy, Professor at the Egyptian Atomic Energy Authority, I would like to thank her for this valuable scientific contribution, which clearly reflects the strength of applied radiation research and its connection to real industrial and technological needs. This work represents an important step in linking fundamental radiation chemistry with practical dosimetry applications, and it is a great example of high-quality research produced within our national research institutions. I would also like to extend my sincere thanks to all the followers of For Science Salah Lotfy channel for your continued support and interest in science and technology. I invite you to share your scientific opinions, write your comments, and discuss this research in the comments section below the video. Your engagement helps spread scientific awareness and supports meaningful scientific dialogue. Thank you for watching For Science Salah Lotfy channel.